Lecture 2, Chapter 2. Hey, it's going to start out with cells. Cells, as you learned in biology class back in the day, fundamental units of life. Organisms have one or more cells. We will talk about little things like Giardia, cholera, things like that, bacteria, fecal coliform down the road. Those are all individual little cells, but they can do nasty stuff to us. Genes. Sequences of nucleotides of DNA, instructions for proteins, create inheritable traits, of course. We'll talk about how DNA, of course, can get mutated throughout the class. Chromosomes composed of those many biology review there. Physical change, no change in chemical composition. So if you take a big piece of paper, rip it up into many little parts, it physically is still the same. It's in little parts, and then you get a lot to pick up, but it's still physically the same. Chemical change is if you take that piece of paper and you burn it, chemically the atoms rearrange in there. We get a nice little exothermic reaction, and boom, something different. Nuclear change, radioactive decay. Keep in mind it takes about 10 half-lives for our nuclear waste to become stable. That can be thousands and thousands, if not millions of years. We focus on nuclear fission because our nuclear power plants are nuclear weapons, but more so our nuclear power plants actually act with fission. The sun is what involves. Kinetic versus potential energy. Back to your days in physics or 8th grade or something when you learn this. Energy, that's kinetic, is movement. Energy of movement. Heat is given off oftentimes as a result of this. We can also get the electromagnetic radiation. If you look at something very interesting, as I just noticed, this bottom little electromagnetic radiation, of course, is given off in waves, which waves move. That's kinetic energy. It's actually upside down, which is really interesting. Anyway, a spectrum of that electromagnetic radiation is our visible light. One thing we'll kind of talk about, which is upside down here, is gamma rays. Gamma rays will penetrate that DNA we talked about before. UV rays, for example, can cause things like skin cancer. Potential energy is stored. Oh, hey, back to the kinetic energy. This is actually kinetic energy right here when that baby is moving. We've got lots of windmills in our region. Awesome. They can power up to about 400 houses per day when they are fully engulfed in kinetic energy. Potential energy, this water right here behind the dam has potential to create electricity. Renewable energy versus non-renewable. Renewable is gained from resources that are replenished by natural processes in a relatively short time. Generally within a lifetime or so, that can be replenished. Trees are an example. Non-renewable energy can be depleted and are not replenished by natural processes within human timescales. So an example, of course, is oil, coal, and natural gas. We are using it up way too fast. It is not sustainable for future ends. High quality energy versus low quality energy. High quality energy, you can see the coal burning on the picture on the right. What that is it's very condensed carbons, and that releases a phenomenal amount of energy. That has a high capacity to do work. It's very concentrated. They used to use it more, but even still today, you can actually use coal. It gets so hot to liquefy a lot of metals. Low quality energy, a good example is the ocean, because the ocean does have energy, but heat energy, for example, but it's very huge body. First law of thermodynamics: energy is neither created nor destroyed. We are considered to be a closed system for the amount of matter we have on our planet. Energy is a little tricky because we do get energy in from the sun. Second law of thermodynamics is a little bit more important to this class because second law of thermodynamics, energy always goes from a more useful to a less useful form when it changes from one form to another. What that means is this. What happens is we get the sun's energy, it goes into the grass, we have net energy lost. And when it goes from this to the cow, what happens is, remember, in a food chain, only about 10% of the energy carries through. A lot of it is lost as heat in this case. A lot of it is excreted as waste. That is the biggie associated with the dynamics with the food chain. A system is a set of components that interact in a regular way. For example, the Earth. If you look at the picture on the right, we've got the Earth in the middle, check. And what happens is we've got glaciers, we've got lithosphere, which is tectonic activity, volcanism, biosphere. Bio means living, the living parts of our Earth. our atmosphere, our hydrosphere, our lithosphere, all that stuff working together in a complete system, and they need to function in balance. Feedback, we'll hit in a second, any process that increases or decreases a change in a system. Before that, we have input into an environment. Well, into an environment, think about a river system as an environment. What happens is we have energy go in. We've got little plants growing in a river system. So what happens is the sun's energy goes in and creates those little plants or helps those little plants grow. We get matter going into that. Nutrients go into those little plants. We get information. Not kind of sure what kind of information goes into it, but live with it. Throughputs are system processes. So that what that river does on a daily basis, it creates glucose, it creates oxygen, it supports life. What do we get out of it? Well, the worker products are the glucose and the oxygen. Unfortunately, a lot of times in our systems, we do get waste and pollution. If you look at a big city, an urban city rather, versus a rural area, what happens is we need a lot of input going into an urban area because they don't tend to grow their own food. We also get a lot of waste and pollution out, plus we get a lot of wasted heat in a lot of these systems too. Positive feedback versus negative feedback. Positive feedback, a system is going to change in the same direction. This can cause major environmental problems. For example, as our temperatures get warmer, what happens is we get less snow and ice. What happens is snow and ice, as you know, you have to wear your sunglasses in the wintertime around here. We have this thing called albedo effect. And what happens is the albedo effect on the snow bounces off and bounces right back into space. Well, what happens if we have less snow is we get more sunlight that's absorbed and stays on the earth. What happens is that's a positive feedback loop. We get warmer climate. Negative or corrective feedback loop. I'll show you a picture of that one. Let's say on the positive one real quick. This is the example that was given in the beginning of the book. What happens is if we cut down the vegetation around this water area, which is called the riparian area, by the way, what happens is we get increased amounts of erosion and nutrient loss. So we get more and more erosion. What happens if we get more and more erosion is we don't have nutrients and then trees can't grow. Well, what happens is then more vegetation dies and it just keeps going and going and going. That's a positive feedback loop, keeps direction. Negative feedback loop is like in your house. What happens is your thermostat, and hopefully you have a digital in your house you can program, because this one is what happens when it reaches 70 degrees. It says, whoa, stop. And what happens is it turns off the furnace. So the furnace will cool down a little bit. Then if it cools down to like 68 degrees, it's like, whoa, we want to be up to 70 degrees. So it actually turn on. A negative feedback loop stops and it goes in the opposite direction. Time delay, amount of time between the input of a feedback stimulus and a response to it. Classical example is predator-prey relationship. So what happens if we have a coyote and a rabbit? So what happens is the rabbit population goes up. What happens is the coyote population is going to go up, but there's a little time delay in between there, and that's called a lag time. What happens is then, as the rabbit population goes down, because all the coyotes are eating them, we'll have a little lag time or delay time, and then that will follow. We'll talk about that when we do climate change too. Tipping point is also known as a threshold point, where all of a sudden you reach a point, boom, done, something's going to happen. With the idea of climate change, scientists fear we're almost at a tipping point. What's happening is the oceans can only absorb so much CO2. They turn it into bicarbonate ions, and what's happening now is they think it's going to start rejecting it because it's reached its tipping point, it's reached its maximum. Think about it as, if there's that kid in class who just kind of drives you nuts, what happens is you have a tipping point, you have a threshold point, and then you just need to get up and move someplace else. Synergistic interaction and synergy. Synergistic reaction is two or more processes combined in such a way that combined effect is greater than the two separate effects. So, what happens is, in the real world, if we get air pollution, if you live in an urban area, you probably have a little bit more air pollution. What happens is you also get water pollution. What happens is those two things come into your body and make the effects worse. So if you get headaches, you might get even worse headaches. You might get worse fatigue. And then we get soil contaminants coming in, and you ingest those things so you don't feel good all the time. Two or more things come together and make the worse. Altogether, Chapter 2, the Hubbard Brook Forest Experiment and Sustainability Practice, where they cut down a bunch of vegetation, revealed that clearing a mature forest degrades natural capital. Of course, natural capital are the resources that we need. How far can we go expanding our ecological footprints without threatening our quality of life is really the question. So, something we talked about in the previous chapter is this thing called ecological footprint. Well, the more affluent we become, the more resources we use. How far can we push that? We really need to strike a balance with nature because we don't want to reach that tipping point and have our populations crash. Hey, that's it for Chapter 2.